This video is covering a couple of topics in trigonometry that will be useful for our analysis of serial planar manipulators. Specifically, we're going to look at the inverse trig functions for sine and cosine and solving equations with sine and cosine. Now, if we have an angle shown here in the xy plane, so here's our angle, we'll call it theta. Then if we go ahead and draw a right triangle, we know that the following is true. So we know that cosine of that angle is equal to the ratio between this adjacent side and the hypotenuse. And likewise, we know that the sine of the angle is the ratio between the opposite side and the hypotenuse. So if we have these ratios and we want to find out what the angle is, we can use the inverse trig functions. Like that. However, there are two angles that satisfy this equation. So for a given ratio here, a over h, there are two angles, theta, that satisfy cosine of theta is equal to a over h. Let me illustrate. Here again is the xy plane. So here's our angle, theta. And in this case, a over h is going to be a positive value because a is a positive x value and the hypotenuse is always positive. So an identical, or an angle that would give you an identical ratio, a over h, would just be the positive value of that. And when you use the inverse cosine function, so first of all, either of these two equations would give you the same value for cosine of theta. I'm sorry, either of these two angles would give you the same value for cosine of theta. I mean, assuming this one is just the negative of this one. They're not quite drawn to scale. So when you use the inverse cosine function, the calculator makes an assumption about which quadrant your angle is in. So it's always going to return to you, if you have a positive ratio here, it's going to return to you an angle in the first quadrant. So this here is the value that inverse cosine of theta would give you. So even if your angle actually was in the fourth quadrant, your calculator is always going to tell you it's in the first quadrant. And now let's just look at the other cases for if our actual angle is in, say, the third quadrant. So here we have this negative angle. Now here the cosine of this angle is a negative value because it's a over h. So a is negative, and so cosine of this angle is going to be a negative value. There's another angle that could give you a negative value like that, and that's this angle. So again, and when we use the inverse cosine function for a negative value here, we're going to end up with there are two angles that could satisfy that equation, and the calculator is going to assume that our angle is in the second quadrant. So our angle actually could be in the third quadrant or it could be in the second, but when we use the inverse cosine function, the calculator is going to assume it's in the second quadrant. Now we'll look at the second and first quadrants. So if our actual angle is in the second quadrant, like this, the cosine of that angle is going to be a negative value. And we already said that inverse cosine assumes when it has a negative value that the angle is in the second quadrant, so it's going to give us the correct value this time. And then the first quadrant is the same thing. If we supply a positive value to the inverse cosine function, then the calculator assumes that our angle is in the first quadrant. So it will give us back this, it will give us back this angle in red. I'm not drawing that very well, but it's supposed to be the same angle. Anyway. And then, so the inverse sine function behaves similarly. Because there are two angles that can satisfy this equation, sine theta. So if we start out, if our actual angle is in the fourth quadrant, the sine of that angle is going to be a negative value, because here the opposite is a negative y value. So another angle could satisfy that, and that would be an angle here in the third quadrant, because it would form a triangle with a negative y value. Our calculator is going to assume, in this case, an angle in the fourth quadrant. So in this case, the calculator is going to return an angle where it should be. And if our actual angle for another scenario is in the third quadrant, then that would give you a negative value if you took the sine of this angle, because the opposite side is negative y. But we just said that our calculator for a negative case assumes we're in the fourth quadrant, so this is what the calculator would return. And in the second quadrant, we have here a positive value if we take the sine of this angle, because the opposite side is positive. And so for a positive case, the calculator assumes that we're in the first quadrant. So it would return this angle. So if we took the inverse sine of this ratio, then the calculator is going to give us back this angle here in red. And then finally, if our actual angle is in the first quadrant, then the calculator will give us the correct value when we take the inverse sine. So we have these different scenarios. So if one thing, I wrote 0, but it should say theta. One thing that we can see from this is if we have the value here for opposite over hypotenuse, if we know that ratio, then we don't really know the angle. We only know it's one of two cases. So if opposite over hypotenuse is a positive value, we know the angle is either this here or this here. So it's the calculator is always going to return something in the first quadrant, but we don't really know if it's in the first or the second quadrant. So in order to determine what the angle actually is, we need to have both A over H and O over H, so that we can sort of narrow down the possibilities. So if we have A over H and O over H, if we have these ratios, and we use the inverse cosine and inverse sine functions, and they return to us angles, one in the first quadrant and one in the fourth quadrant, then we know the actual angle is in the fourth quadrant. So for that case, we can just take the value returned by the inverse sine. since that's going to give us the right value. And then if we use the inverse cosine function and it gives a value in the second quadrant, and the inverse sine function and it gives a value in the fourth quadrant, then we know our actual angle is in the third quadrant. So for this case, we can take, we know that theta is equal to um, 180 minus the value returned by inverse sine theta. So that would give us this angle here. So it's because the value from inverse sine theta in this case is going to be negative, because it'll say a negative angle. So for this case, the actual angle is 180 minus the value returned by inverse sine theta. So what we're doing is looking at how to determine the actual angle given these ratios. Okay, now the third case, where our actual angle is in the second quadrant, in that case, inverse cosine will give us a value in the second quadrant and inverse sine will give us a value in the first quadrant. So if we use these two functions and inverse cosine says it's in the second quadrant and inverse sine says it's in the first quadrant, then we know the actual angle is what's given by inverse cosine. So we can listen to inverse cosine. And if both values returned are in the first quadrant, then those values are the correct angle. They're the actual angle. So we can just say it's the inverse cosine again, or inverse sine. They're both correct in this case. So this is just a tiny topic on using the inverse trig functions to find out an angle. And we'll see in the next video more how to use this for the application of robot kinematics.